Hi, I'm Ravi Subramanya. I work for GEICO Tech. Today we will be talking about centralized telemetry and security enforcement using SONiC and P4. The agenda is mainly about the GEICO network components, how we basically have set up the SDN controller and managing the SDN SONiC switch fabric, and couple of use cases, related to, how we solve using P4 programming and SONiC pins components and pins and PSI dependency and pins driver dependencies also will be discussed as part of this presentation. Yeah, GEICO network components, basically it presents a high-level view of SONiC switch fabric and a set of key SDN components which basically ensure the health, security, and performance of the switch fabric. Switch fabric here is data center network infrastructure, which is built using community SONiC software. And the main SDN basically allows here to configure the SONiC switch. And in addition, it also basically helps to program the flow rules, which actually controls the packet forwarding, and also helps to retrieve the stats and the device health using the GNMI telemetry. So, SDN is the network. There are about multiple components as part of the SDN, and one of them, the components here are the network switch inventory is the central component which houses the information about the switch details as well as the cabling required for the data center, and that basically establishes the baseline for all the when we need to compare the observed state or the real-time state of the hardware. And observability is where monitoring happens, and this is the component that establishes the communication with the SONiC switch to get the GNMI telemetry information on a continuous basis, and it passes down the information, the feedback to the downstream components like operations and automation to do their respective workflows. It also basically gets the delta, finds the delta between the intended and the observed states in order for to apply any change in the intended behavior or to apply any new rules in the SONiC switch. The operations module executes the workflows passed down to it, from the upstream observability, where it modifies the intended state of the switch, and also it also performs the role to do some initialization with respect to programming the flow rules through the automation on the switch. And automation is where the intelligence lies, with after once it receives the feedback or the instruction from the operations, would initiate the P4 programming of the flow rules on the switch. And of course, it also supports configuring the switches using the GNMI. This is one of a use case where how security enforcement is kind of we can take a use case here, where observability platform monitors on a continuous basis and the network traffic using network traffic, and gets and gathers the IPFix records from the switch. And this is one of the examples we can take is TCP SYN flood is a scenario where it's a denial of service attack, which is basically that sends a massive number of the SYN packets and without acknowledging them, I mean, to the back to the switch. This would basically create like a large number of half-open connections in the switch. And how we basically alleviate and how we can remediate this problem with the help of the telemetry is to use the IPFix data received from the switch on a constant basis, and detects a large number of half-open sessions and raises an alert to the system, and also helps to configure the ACL rules that actually blocks the source, the traffic from the source, and sets its drop action for all the traffic. There could also be a scenarios where we have like a number of multiple client sessions with different client IP addresses. In such a case, it raises an alert to basically update the configuration on the SONiC switch. That one of the use cases how we can actually solve with the telemetry. Another use case where we can actually do the smart network remediation. This is a scenario where observability again gets basically this monitors the device, and it gathers stats, device health, interface counters, route tables, and all these stats from the switch using GNMI. And one of the scenarios here is when a link flap happens on the switch. There could be scenarios where the route table basically may have a missing route causing some traffic loss, and this can be detected by the centralized telemetry using the route table information it gathered from the switch, and would actually compare and find the missing route, and this will enable the automation workflow to basically program that layer 3 flow rule in the SONiC switch, and thus it basically remediates the loss of route scenario here. This is it's about James.
Okay, now I'll discuss more on the device side. Just to start off, I guess GEICO right now is trying to build the on-prem cloud network. And we're trying to use open source code and build our own internal technology for deploying. And for switches and routers, we're using SONiC, one of the leading network operating systems that is out there. Already Shweta talked about using it for Dash, and we're planning to use it for switches. So GEICO SONiC, we're building it based on open community SONiC source code, which is available. And we're integrating our GEICO features and fixes to that, and integrating with the vendor SDK, which contains SI and platform packages. And that completes the GEICO SONiC. And we'll be using pins, which is based on P4, to enable controlling forwarding, setting up the forwarding tables, as well as other things to set up the switch. So quickly, I want to go over the components of pins, and so that we can talk more on later slides. So pins has a P4 runtime server in the application layer, and that P4 runtime server contains a couple of components. It's got a component where it can take the P4 runtime messages and add it to P4 RT tables inside the app DB. And it also has a component of listening to the GNL packet family messages, which is to be sent it to the GEICO controller. Also, it is able to get the packet IO messages from GEICO controller through a P4 runtime, and send it out, transmit packets through the NetDevs. So that's the largely the function of P4 runtime server. And the P4 org agent, which is part of the Swiss layer in the middle, it takes the P4 objects that is in the P4RT database in AppDB and maps that into SI objects. So this is one of the critical portions of the pins. And once those entries are made in there, then the syncd component, which is part of the vendor SDK, takes the SI objects through the SI interface and makes call into vendor SDK API. And the vendor SDK API is then mapped into driver and hardware API. So the kernel and also as part of the vendor SDK, there is kernel drivers and modules that the vendor has. So in the case that we have at the time when we were working on this, we didn't really have a source code access to the vendor SDK. That's why they're colored red in those boxes. And we'll be talking a little bit more about our experiences that had, as well as that we had by using code that we don't have access to source code. And we certainly heard good news that Tofino, all the stack will be available. And definitely that is, we feel that is the right direction that the community should go. And I think you'll hear some of the issues that we ran into when we don't have source code. So the initial GEICO pipeline that we're targeting is basically to do routing and the ingress ACL. So we've taken the already upstreamed P4 pipeline and pins and work with that as much as possible. And so initial thing that we wanted to do was to do a routing, which we didn't really have much of an issue. In the pipeline here that you see, this is the upstream pipeline that is upstream. You see that there's after the parser, there is a pre-ingress ACL stage and L3 admit routing and WCMP group and next hop neighbor and ingress ACL, and followed by mirroring and the egress stage. So not programming anything else, just L3 admit routing and skipping the WCMP group table and next hop neighbor and just programming those. We were able to get the routing done and we didn't have any issues. The issues came when we were trying to work with the ingress ACL, program into the ingress ACL. And this was to kind of color what we're trying to do. We were trying to have packets, LLDP packets and ARP packets sent up to the controller so that we can build a network topology based on these packets that we get. And when we try to program the ingress ACL to punt the packets to the CPU, we saw that the pre-ingress ACL was being actually created. And it was as if there was some sort of dependency of pre-ingress ACL to the ingress ACL, and which really isn't the case. And one thing that, so we started off not programming the pre-ingress ACL, just programming the ingress ACL, try to make it work. That didn't work. And next best thing then is to remove the pre-ingress ACL table from the P4 program itself and from the pipeline programming itself and see if that would work. And that also didn't work. And we ended up actually removing the pre-ingress ACL code from the P4. And it's probably just one instance of it, but it does highlight an issue of needing to represent the right SI object dependencies in the P4 program as well as the P4 org. And so that's one thing that we feel, that at the design level, that should be done that way, make it explicit. Also, it'll be useful to have explicit SI object dependency represented in the P4 org to make it more strict. And some of these kind of recommendations are coming from because we didn't have the source code access in the syncd layer and SI adaptation layer and below. This was more needed for our use. And certainly, once again, I think we welcome the trend to open up source code for SI and below and all the stacks. Another thing that we try to do is, as I mentioned before, build a topology, network topology based on LLDP and R packets. So that required packet punting from the ASIC into the CPU. So once it gets to the CPU, a vendor driver takes that packet and sends it up to P4 runtime server. So it can be sent as a packet IO message to controller. And the pin spec recommends doing it from the vendor driver. Of course, at the time, we didn't have access to the vendor driver, so this posed a problem. And what we ended up doing is hooking into NetFilter pre-routing hook, creating a small module and generate the necessary general packet message and send it up to the general packet receiver that's in the P4 runtime server. And in general, as there are still vendors that haven't opened up the source code, I think in general that we would recommend having a framework that is vendor independent, something like a NetFilter, hooking into NetFilter, something that is a vendor independent mechanism in place is something that we like to see. And not just for naked general packet NetFilter, but other mechanisms as well. So that's something that we really would like to see. And I'd like to talk a little further also some of the things that we haven't done that we haven't highlighted here. We have worked on more on the general packet and we added some tools, for instance, to capture general packet that are coming up to the user space to put it into PCAP files to be able to see what has come up, make it easier. And we also made some patches into pins code and general packet code. And we plan to upstream those. We're working on upstream those code. And going forward, the version that we are working with is quite old. It's a SONiC 2305 version. And if I look at the SONiC pins repo these days, almost every week there's some commits that are going in, very active commits happening. And we love seeing that, and we're eager to move to the latest version of SONiC pins, and also try to implement the VXLAN tunnel there, so that there are use cases that we really like to enable through that. So something that we're looking forward to do. Now, so one of the issues that we do see though is that the accompanying P4 orchestration code that goes with the that SONiC pins commits that are happening, it's hard to find and hard for us to actually try out the code. And we'd like to try that out as soon as we can. So this is something I think sort of having all the code available early is something that we would really like to see. And yeah, we would also really like to see the SONiC pins effort be collaborated, and we like to collaborate in this effort with the community. That's it.
Thanks. Any questions for the last? Yeah.
It's really awesome to see you using SONiC pins. I'm one of the founders for SONiC pins. Really appreciate, let's connect. And most of these things we would like to upstream. Pretty much all the P4 exchanges we would like to upstream. We have been doing that. You've probably been seeing some updates in the community recently. In terms of the using, the driver to the packet punting. That's because in pins, we wanted to get some ASIC specific fields also in that path. Get more information about, for example, if a packet is forwarded through the ASIC, capture some of that information as well. And we could explore how we can do that a little bit independent of the platform. I had a question about your opening up the SI and etc. Are you looking for opening up SI API, adding more things into the API, or also looking for SI implementation? Because I understand SI implementation and SDK is generally closed source.
Right. So I think from someone who's trying to use this code and then deploy, I think we generally agree that SDK and below, where the sort of the hardware mapping is done, I think it's it's close. But I think there is actually room for opening up the SI to SDK mapping to the community. The more that we know, the better. And actually, because I was at Intel, I have seen the implementation of SI to SDK mapping, and it's a really useful tool for deployers to see. Because I think at the end, providers, I want to see something stable and that can be deployed quickly. And having access to the source code as much as possible really helps in deploying a solution like pins in the network.
Thank you.